Black holes are among the most fascinating objects in our universe, and also the most mysterious. A black hole is a region in space where the force of gravity is so strong, not even light can escape. The holes haunt our universe. Dark centers of gravity that swallows everything in their path. The history of black holes isn't very long. 100 years ago, no one knew about them. Because of Einstein's general theory of relativity, black holes were later discovered. The general theory of relativity was developed by him in 1915. It explained that other forms of energy, such as sound, heat, or light, are affected by gravitation as well. This was another conclusion drawn by Einstein. Gravitation affects almost everything. Not only are physical objects attracted by the force of gravitation, but they also attract heat, sound, and light as well. This means that there can be such objects in the universe that have such a high gravitational force that they can completely absorb light. If there were such objects, they'd be completely black. We won't be able to see them, because not even light can escape them. This is exactly what black holes are. But when Einstein presented his theory of general relativity, the concept of black holes was merely theoretical. By the 1960s, researchers and scientists had finally agreed that not only theoretically, but perhaps one day, realistically, we would be able to see black holes. The term black hole was used for the first time by a magazine in 1964. But only after 1967, this term gained popularity when physicist John Wheeler popularized it. Even though the term black hole sounds quite sensational, it is a misleading name. It might sound like there's an actual hole there. But that's not the case. There's no hole in the space. Stars form black holes. So there's some material at its center. But in the stars, even though our sun is a star, there's a continuous nuclear fusion reaction at their center. These reactions produce heat and light. The heat being produced sends a force outwards, and at the center of the star, there's the force of gravity. This helps the star remain intact and alive. This is how the stars maintain equilibrium throughout their lives, the forces pushing outwards due to the reaction, and the forces pulling inwards due to gravity. But these reactions take place when a fuel exists. It would get burned up at some point. And when the fuel ends, there would not be any forces pushing outwards. And the gravitational force pulling inwards wouldn't be countered by an equal force, so the star will collapse on itself, because of its gravity. This will take a long time. It depends on the mass of the star. If the mass of the star is not high, it turns into a red giant, after which it can become a planetary nebula, or a white dwarf. But if it was a huge star, a star would have a lot of mass. When it runs out of fuel, it cools down, and turns into a red supergiant. And then the supergiant bursts and turns into a supernova. After this, a tiny core remains. If the core is tiny, it is called a neutron star, but anything bigger than that, we call it a black hole. Speaking of the mass of the star, after it collapses due to its gravitational force, becomes small, and condensed, it can turn into a black hole. But the interesting thing here is that our sun will not grow into a black hole. This was proven by an Indian-American astrophysicist Subrahmanyan Chandrasekhar. He developed the Chandrasekhar limit value. He said that the maximum mass of a white dwarf can be 1.4 times the mass of our sun, above which, it cannot be stable, and would turn into either a neutron star or a black hole. But since our sun, the sun, is under this limit, it will become a white dwarf, instead of a black hole. There are mainly 3 to 4 types of black holes, stellar and supermassive, black holes being the most common. Stellar black holes form when massive stars die and collapse. They're roughly 10 to 20 times the mass of our sun, and scattered throughout the universe. There could be millions of these stellar black holes in the Milky Way alone. Then there are the primordial black holes. These black holes are as small as an atom, but their mass is like that of a mountain. It is an assumption that they are as small as an atom. These black holes are merely theoretical and hypothetical. Supermassive black holes are giants, by comparison, measuring millions, even billions of times, more massive than our Sun. Sagittarius A, the supermassive black hole at the center of the Milky Way, has a mass of roughly 4 million suns, and has a diameter about the distance between the Earth and our Sun. There may be a fourth type of black hole too. Though it cannot be said for sure, no proof of it has been discovered yet. Because black holes are invisible, the only way for scientists to detect and study them is to observe their effect on nearby matters. The black hole isn't like a big, black ball that sucks everything around it. Proposed by physicist Stephen Hawking, Hawking radiation is a theoretical prediction that black holes are not completely black. Due to quantum effects near the event horizon, black holes are expected to emit radiation and gradually lose mass over time. The boundary of a black hole is called the event horizon, a point of no return, beyond which we truly cannot see. When something crosses the event horizon, it collapses into the black hole's singularity, an infinitely small, infinitely dense point where space, time, and the laws of physics no longer apply. At the center of a black hole lies the point of infinite density known as a singularity. The laws of physics, as we currently understand them, break down at this point. It's important to note that singularity is a theoretical concept, and our current understanding of physics cannot accurately describe what happens under such extreme conditions. Black holes consist of accretion disks, particles that form when gases and dust fall toward a black hole. In this disk, the particles on one side are brighter than the other side. There's a simple reason for that: the particles spinning towards us seem brighter to us, and those spinning away from us seem dimmer. This is due to the Doppler beam effect. Everything is black beyond this point. One thing is sure here: if we fall into a black hole, the chances are that we will disintegrate into pieces due to the gravitational force. We will die in milliseconds. But even there is no need to be scared of black holes. Earlier, many people had this misconception that the black holes suck up all matter, keep getting bigger, and eventually, it will end the whole universe. But that's not how it works. At the center of each galaxy is a supermassive black hole. And all other planetary bodies and stars in the range of the black hole revolve around it. In the same way that all planets in our solar system revolve around the Sun. The same thing happens at the center of the galaxy. In conclusion, if we maintain a proper distance from a black hole, we will be safe and secure. Understanding black holes is an ongoing area of research, and advancements in observational tools and theoretical models continue to deepen our knowledge of these mysterious objects.